This will be a presentation on energy production, and it will be co-presented by Jason Crawford, Will Regan, and Eli Dourado. Jason is a writer at The Roots of Progress, where he writes about the history of technology and the philosophy of progress. He's a part-time advisor to a role in data, and he will be talking about bottlenecks in nuclear fission. Will Regan is project lead at Google or Alphabet X, their moonshot factory. In the past, he has worked at ARPA-E on, among other things, nuclear fusion, which is the topic of his presentation. Eli is a senior research fellow at the Center for Growth and Opportunity at Utah State University. And he worked previously at Boom. He wrote a paper arguing for a more reasonable regulation around supersonic flight. He'll be talking about advanced geothermal energy. So, Will?
Yeah, thanks a lot. So I'm Will Regan. I'm currently at Google X, starting up a range of energy, agriculture, and climate-related projects. I'll kick off this energy production session with a talk on fusion, followed by Jason on fission and Eli on geothermal. And I think the theme that connects all three of these is that each of them is a truly enormous clean energy source. And if we can get through some of the challenges in each of these fields, we can pave the way to a future of much more abundant clean energy that's also cheap. So when I say abundance, I think we should aim high. We shouldn't just aim to replace the fossil capacity we have today with cleaner sources. We should assume that humanity's power appetite is going to continue growing. So maybe let's aim for about 10x where we are today. So from 20 up to 200 terawatts, but swapping fossil for much cleaner sources that are less resource intensive. And in addition to just having raw power capacity, you want a good buffer in your system so that it's very reliable and something kind of like our oil reserves of today. So it would be great to have a reservoir that's, say, like a month of that power use. So that's about a half a zettajoule. And where we are now is, depending on how you count it, we're between 1 and 4 terawatts of clean sources out of a total of 20. That's not a bad start. Where we're in trouble is that if you set aside fossil as the buffer and biofuels can't provide all of your solutions, really the only energy storage we have now is things like pump hydro and batteries, which I think their total capacity is around 10 terawatt hours, which is 30 minutes of global energy use. So this is all the options we have to work with here. This is a plot of all the exergy flows in and out of Earth and all of the accumulations in reservoirs. So all of the things on the top of this are the sources that are driven by sunlight. So you've got all of your renewables up there, solar, wind, hydro, and then you've got all of the biological accumulations of solar energy. So things like biofuels, biomass, crops, as well as all of the ancient solar energy that's sitting in fossil fuels. And if you assume that renewables can't power the entire world and you're leaving fossil off the table, we really only have 3 gigantic sources that can provide the bulk of our energy system. And that's the 2 nuclear options, so fusion and fission, and then also geothermal energy, which, as Eli will discuss later, we're really just scratching the surface of that. Okay, so now on to fusion, which is what powers all the stars and our sun. Fusion could be an incredible energy source. The fuel is essentially free, unlimited. It's extremely energy dense because it's a kind of nuclear energy. It's about 1 million times more energy dense than chemical fuels, and it emits no greenhouse gases. The gist in fusion is you're trying to take light elements like hydrogen and squeeze them together to form a heavier element, and then like helium, and then release a lot of energy. If you engineer it right, most of your byproducts are benign, helium, protons, and energy, and you only generate some short-lived mild waste. We're literally swimming in fusion fuel, so the amount of trace deuterium that's in everyday, like a gallon of drinking water, is equivalent to about 8 barrels of crude oil. And you can do other things besides make really great power reactors with this. You can use fusion to make very mass efficient propulsion for rockets to go to deep space or to defend Earth against rogue comets. The problem is we have this awesome fuel, but no one is going to burn it if your reactors are complex and super expensive and they break all the time. And unfortunately, with the paths we're on now, that's kind of where we're heading. But that doesn't have to be the case. So I'll step through the basics of fusion and discuss ways that we could just do better. So in fusion, like I said, you're trying to get light elements to stick together. Nature's made this kind of difficult for us by putting a big Coulomb barrier in the way. So if you think back to like the activation barrier for chemical reactions, you have to get wood or gasoline up to several hundred degrees for it to start oxidizing. It's a similar thing for fusion, except the barrier is 1 million times bigger. So you have to go up to like 100 million degrees. And most of the time when you collide light elements together, they scatter, they don't fuse. So you end up having to make a very well-insulated thermal reactor system. So in a sense, there's nothing to fusion. It's just a really hard engineering challenge. But we're pretty good at driving energy into hydrogen. The question is, how do we design a little box that can contain this energy and not leak it all out before you get enough fusion reactions? And we've identified two pretty good ways of confining fusion fuel, so magnetic fields and inertia. But unfortunately, the flagship experiments to prove these out have become these massive multi-generational mega projects that are just sucking up all the resources. And on one hand, you have magnetic confinement. So in this, you heat up your hydrogen, turn it into a plasma, which is the nuclei and the electrons sort of floating around as charged particles. And then you use magnetic fields to keep these charged particles confined and away from the walls as you keep driving more energy into it. The leading experiment here is the ITER tokamak being built in France. And we kind of got stuck on this path because we got really good results in the 70s. People kept plowing more money into it and building more tokamaks. And it just turned out that the way that it scales with the old conventional design, it cost tens of billions of dollars to get an energy positive facility. So that's really slowed down research. It's really diverted the whole community of researchers onto this project. And on the other extreme, you have inertial confinement, where you're essentially doing adiabatic compression. So you take a little pellet of your hydrogen and squeeze it with this really intense burst of like 1,000 terawatts of laser power for a brief instant. And again, we're in a similar situation where the flagship experiment, the National Ignition Facility out in California, it's gigantic, it's expensive, it's a very complex system, and it's taking a long time to make progress. It may never even reach the ignition, ironically, despite the fact that it's in the title. So neither of these, while these are doing a good job of proving that these are effective ways of confining the fuel, neither of these is going to lead to a practical reactor that's cheaper than natural gas turbines. So this brings me to the first bottleneck in the field, is that in addition to studying the mechanisms of confinement, we need actual practical research paths that can get us to a demonstration of being energy positive that don't cost tens of billions of dollars and take 20 years. So if you want to find a better path, you can do just a first principles analysis of say this is my fusion plasma, it's a blob this big, it's got a certain density, it's got a certain amount of magnetic field, I'm squeezing on it in this way. And you can make a relatively conservative cost model where you just extrapolate the physics down from ITER and NIF, these mega facilities, assume you have the same kind of cost overruns. And it turns out that in the density range in between these extremes, where you use a little bit of magnetic and a little bit of inertial confinement, you can be 2 to 3 orders of magnitude lower cost and get the same kind of energy break-even performance. And one other thing to note here is that magnetic confinement is operated at very low density and steady state. But as you move to higher and higher densities and move to the inertial regime, you have to switch to pulsed operation because the static pressure just becomes too high. So it's kind of on the left-hand side, you've got coal burners or campfires, and on the right, you have internal combustion engines. So that's the parameter space. How do we find better paths within that? So option one is you take kind of a conservative, mature approach like a tokamak and be smart about making it smaller and cheaper or less complex. And that's what groups like Commonwealth Fusion out of MIT are doing. Another option is to just look at this, look at the sweet spot in density where you can be 2 to 3 orders of magnitude lower cost. And some of these approaches, in addition to being inherently lower cost, they can also have some engineering advantages when you try to build an actual reactor out of this. And some of that arises from them being pulsed. Back when I was at RPE, I helped set up a program called Alpha to support a number of concepts in this space. And there are a few good startups and a few good academic and national lab projects in the space. But none of these alternate paths are still getting the prioritization they need. All of the resources are still kind of going into the mega projects. And then the second bottleneck is kind of a future one. So even if we manage to get to a demonstration of energy positive fusion experiment, it's not going to matter if it doesn't lead to a practical reactor that outcompetes or is somehow inherently better than a fossil generator. Most people in fusion are just trying to get to that scientific demonstration. I think there needs to be much more focus and probably some hard down selects now that favor approaches that are inherently easier to engineer. So one example of this is there are a few concepts that are trying to use a liquid first wall so that the fusion plasma mostly just sees a liquid blanket around it And when the high energy particles and X-rays come out, they don't beat up the solid material that has to be replaced every couple months. The other approach is you could just look for things that are more efficient at heating the fuel, better at confining it, so that can let you build smaller reactors. You can potentially operate at higher temperature and use cleaner second-gen fuels, and all of this can lead to lower cost plants, easier regulations, and potentially more applications beyond just like gigawatt scale power plants. So to make this more real and not just theoretical, I'll discuss one family of fusion approaches that sort of satisfy these two bottlenecks I just mentioned. And there's one big problem that has to solve, but the approach I'll discuss is called Z-pinches. They can operate at a range of densities in that parameter space, but they can also sit right at that cost minimum. And what Z-pinches are trying to do is you just take a linear column of fuel and directly run an electrical current through it. So think of it like you have a resistor, you're running a current through it, heats you up by Joule heating, and then it also creates an inward compressive force. So you get heating and confinement all with a simple, direct heating, direct electrical heating. And per the second bottleneck, like Z-pinches are also amenable to nice reactor engineering if they work. They could be very compact. They could use liquid walls. You could just shoot a Z-pinch into a big tank of liquid. And they could potentially use direct energy conversion where the charged particles that come out after you fuse, you can capacitively or inductively decelerate them and convert their energy into electricity. I could save you money on a heat engine. The trouble with Z-pinches is that back when they first started doing these in the 1960s, they ran into these fluid instabilities that just disrupt the column and make it fall apart before it can get hot enough to give you net fusion energy out. The good news is that in the recent decades, several groups have devised mechanisms to keep Z-pinches stable long enough to potentially get you to that energy positive regime. A few groups, you can see this chart on the left here is kind of the way that people in fusion track progress. The y-axis is the triple product of density, temperature, and time. If you're able to get to that blue blob in the upper right, you can make a reactor. And interspersed among all of the red dots, which are tokamaks, you can see these three different sorts of Z-pinches have actually gotten pretty good performance. And the one at Sandia is actually within about an order of magnitude of that kind of ignition territory. The last bottleneck is that fusion is just a really hard thing to fit into the existing institutions in energy research. So it's complex. It requires getting expertise across lots of different domains, across lots of different tech readiness levels, like basic science through to, like making scaled components. None of the actors in this space really have either the resources or the right incentives or the flexibility needed to do this. So you can see like everyone is kind of getting stuck at low TRLs. Like even like Commonwealth, which is like the most mature possible concept, no one has yet demonstrated energy positive operation. So I think what is needed is something like a focused research org or a Bell Labs or a Park, where what you do is you have a small set of related approaches that you fund all under one roof. They're able to share all of this niche expertise so that when you get the world expert for something, you're not removing them from working on other projects that would be related. And this kind of structure, I think, for Z-pinches, a couple $100 million in 7 or 8 years would be enough to get you to that demonstration of viability. And then once you're there, then you can actually think about commercializing in a logical way. And like I said, Z-pinches is just one example. There's other concepts where this kind of model could work really well. Okay, so that's my talk. The hype is real. Like fusion is coming. I think we're going to see someone hit break even in the next decade. But if we want it to be more than a scientific curiosity and something that is actually like a major energy source, we have to be smarter about which concepts we're funding, making sure they're going to lead to viable reactors, and then trying to fund institutions that are more effective to pursue this research. Here's my contact for future questions. Thanks a lot to you all and to Boom and the sponsors and organizers. It's really awesome to be here. So, now I'll hand it over to Jason, who can tell you about a nuclear energy that already works.
Thanks for setting up that context, and we'll do questions on all three of these at the end. Also, great to be here. Great to see all of you. So let's talk about nuclear fission. Nuclear fission has clearly stagnated. It was introduced around the 1950s, and it still only produces about 10% of world electricity, has made almost no penetration into other energy applications outside electricity. We don't have nuclear cargo ships or freight trains. And we're still using the same kind of fundamental basic reactor design that was built for US Navy subs, in the 40s and 50s. The dots at the bottom here are the actual deployment of nuclear electricity capacity around the world. The dotted lines are an extension of the trend from the 1960s and the early 70s, where we could have been. The top of this chart is roughly current world electricity usage. So nuclear could have powered the world. The proximal cause of nuclear stagnation is that it is expensive. It is one of the most expensive forms of electricity that we have. So you can see here it weighs in at over $100 per megawatt hour. Most of that is not the fuel cost or the operating cost. It is the upfront capital costs. It is the construction and financing that must be amortized over the life of the plant. You can see here a comparison of construction costs. A nuclear plant is roughly the size and complexity of a coal plant, but costs much more to build per kilowatt of capacity. Costs of nuclear construction were not always the case. So in the early years of the industry, the nuclear industry was rapidly coming down the learning curve. Costs were decreasing by about 25% with every doubling of global capacity. That dramatically reversed about 1970. And the industry experienced negative learning where the costs went up and up with capacity growth. The USA, you can see, experienced this the most dramatically, but no Western country escaped this. So in addition to the cost escalations, there were long delays introduced by regulatory approval and political opposition and obstructionism. Sometimes these were enough to completely kill a plant. So this was the Shoreham plant that was going to be built in New York, began in '66 with a 6-year time frame and under $100 million cost estimate. And after many, many years of delays, finally abandoned 23 years later when the costs had risen to over $5 billion. You can ask me what some of the delays and obstructions were. What went wrong? To very briefly summarize a complex history, nuclear energy technology was born in wartime and made its introduction to the world as a horrifically destructive weapon. It was under the exclusive, tight control of the military bureaucracy for many years. When it finally made its way into civilian uses, it ran smack into the anti-war and the environmentalist movements of the 1960s. These created a highly turbulent and rapidly escalating regulatory environment. Combine this with the fact that the customers for these things are electrical utilities, which are regulated monopolies that have very little incentive to drive down cost, certainly little incentive to fight cost increases that come from political motivation. And in fact, in some ways have a perverse incentive to raise costs because of the guaranteed rate of return that's sort of built into the way the industry is structured. How did the rest of the companies in the industry respond? Well, essentially, they sought profit in regulatory capture. It turns out it is very profitable to retrofit old nuclear plants with the latest safety equipment. It's very profitable to do, billion-dollar waste cleanup projects, whether or not those are truly necessary for human health. The consequences of these decisions have been a large degree of safety theater in the industry. The formalization of this is a policy called ALARA, which stands for as low as reasonably achievable. This essentially says that there is no radiation limit we're going to set that is safe for humans that you have to meet and go no lower than. We are going to continually drive the radiation limits lower and lower and lower beyond the point where it actually matters for human health. Very slow learning cycles in the industry measured in decades. Very little standardization. The nuclear projects in the US tend to be done as these bespoke mega projects with a lot of custom design engineering, which is very expensive. And as I mentioned, no fundamental advancement in reactor design since not the 40s or 50s. Now, there are better reactor designs on the drawing board. Best practice in the field is to do new designs as small modular reactors, meaning we're going to sort of make our components small and standardized so they can be built in factories instead of constructed on site, take advantage of all the economies of mass manufacturing. They can be shipped using normal rail and truck lines rather than expensive special barges or whatever. Most of the new designs feature inherent or passive safety systems versus the active safety of a traditional sort of light water reactor, which relies on pumps, actively pumping coolant through the system. A molten salt reactor, for example, cannot melt down because it is already molten. It also operates at ambient pressure rather than the over 100 atmospheres of the pressurized water reactor. Some of these are claimed to be walk-away safe, as in the operators could literally just get up and leave the building and it would cool itself down. And some of the designs feature far better fuel usage. Now, nuclear fuel is already by several orders of magnitude the most energy-dense fuel that we have in operation, and yet the traditional light water reactor design only uses a few percent of the energy that's in the uranium. So there are designs that use much more of that energy where they don't need to be refueled literally for decades. In fact, some of the designs that have been proposed, the plant is built with a lifetime of fuel built in from the beginning. It essentially never needs to be refueled. Now, the first challenge to any of these new designs is the NRC approval process. For a case study look at NuScale. Now, NuScale is not even building a crazy advanced reactor design. They're just building a different evolution on the light water reactor. They started talking to the NRC in 2008, finally submitted their application at the end of 2016. It took 41 months to review. It was finally approved late last year. Generated 2 million pages of documentation, and took 250,000 review hours. Now, these review hours are billed by the NRC to the applicant. The applicant pays the NRC by the hour to review their applications. Talk about your perverse incentives. So, bottom line, this cost NuScale over $500 million. In an open letter to the NRC complaining about the process and asking for regulatory reform, they deadpanned that the level of effort for reviewing our application, quote, may not be repeatable for future reviews. The problems have now metastasized to the entire industry. It's been a generation or two. Engineers are demoralized, investors are burned, the public has lost trust. Startups, I am told, define success as getting a DOE grant rather than market share. And finally, the greatest trick the devil ever pulled is to convince the world that nuclear is inherently expensive. I actually think there's some really interesting parallels to Blake's talk in sort of these deeply seated wrong beliefs. This has killed nuclear deader than an outright ban ever could have. Right? If nuclear had simply been banned, all the forces of capitalism would be working to unban it. When you convince the world that something is expensive, even the capitalists don't want to touch it. So nuclear's problems are sort of fundamentally political and social. What could we possibly do about them? So first I want to briefly mention, NRC is currently overhauling its rules for advanced reactor designs. They are mandated to do this by recent legislation passed through Congress called NEMA. So there's a rulemaking process going on, supposed to land in 2024. May be possible to influence this through public hearings, through policy papers or whatnot. I'm not super optimistic about this. I doubt that this is going to go as deep as it really needs to see meaningful reform. I think if you were going to go after a big policy reform goal in nuclear, the goal would be to replace this idea of ALARA, as low as reasonably achievable. What it should be replaced with is essentially firm radiation limits set by science and medicine, where we say this is what is needed for human health and safety. You don't have to go lower than this. The obstacle to this is a model of radiation damage called linear no threshold, or LNT. So this, in essence, says that if you expose 1 million people to radiation that is 10% of the normal background levels that we all get just from living on Earth, that is exactly as bad as exposing 1,000 people to a level of radiation that is 100 times background levels. You just multiply those two and they're equivalent. And for human health, it is not at all equivalent. Now, many experts, if you talk to them, will admit that this is sort of a regulatory construct masquerading as a scientific theory. But of course, nobody wants to come out and sort of be the first one to drive that as a policy. It needs a sort of a respectability cascade. So my impression from talking to people in the field is that it would be possible, but very difficult to do this. It would be like a multi-year effort to sort of build a coalition across all of the relevant agencies, talk to people, find the allies, find the people who are, kind of willing to participate in this as long as everybody else is doing it too, and then get them in the room at the same time and agree that we're all going to go forward with this. The other thing that needs to happen in the US is to fix waste management. So right now by federal law, the only place that long-term nuclear waste can be disposed is at the Yucca Mountain Repository, which is not completed and is not likely to ever be completed, is not on track to be completed. Responsibility for nuclear waste is centralized in the DOE, which is under the administration. It's very difficult for them to do anything that is politically unpopular, and what is more politically unpopular than nuclear waste. The best thing would perhaps be to simply completely decentralize it. Short of that, there has been a proposal to create a dedicated organization with waste management as its goal. So just make it somebody's job. This was actually the recommendation of Obama's nuclear commission in 2012. Fundamentally, nuclear needs a PR campaign. It needs to have its image fixed. It has this sort of a very unfair, very negative image. It needs a rebranding. One VC suggested to me the term elemental power, where we package together all the clean, green, renewable things that everybody likes together with nuclear, not without justification, right? One person who's actually making some inroads on this right now is Isabel Bomeke, a Brazilian model who decided to take her 30,000 some Instagram followers and use them for a cause that she believed in, which is the message that nuclear energy is clean energy. That is her over there. She's totally self-funded right now, by the way, so I think a great kind of like short-term project would be just to like fund her content production. But political change is difficult, slow, and uncertain. So let's wrap up by looking at some ways that some startups are trying to make progress even in the current political context. One approach is to build microreactors. The case study here is Oklo. So they are building a 1.5 megawatt reactor. They call it a nuclear battery. It's one of these designs that doesn't need to be refueled for like 20 years. 1.5 megawatts, by the way, is like 100 to 1,000 times smaller than a typical like large power plant. To have a customer for this, they're going off-grid. So think of remote mining and drilling towns that are reliant on like diesel generators for electricity. Those are going to be the first customers. This allows them to be very low capital costs, to get very short feedback cycles, right? So it's just make everything small. Also, of course, going off-grid means they can avoid the politics and the bureaucracy of the utilities. They have a very interesting approach to the regulatory risk. They actually believe that most companies are making things way too hard on themselves when it comes to NRC approval, that you can do it with a much more minimal application, and that you just don't need to generate 2 million pages of documentation. They have submitted their application at a cost of $10 million, which is considered extremely cheap. It was accepted by the NRC. That doesn't mean approved, just like accepted for review. We'll see how many years and how many hundreds of millions of dollars it takes them. I'm rooting for them, but I'm not optimistic given NuScale's experience. So the other approach is basically to ditch the US and try to find another venue that is friendlier. So Thorcon, for instance, is building a thorium-fueled molten salt reactor, and after going to the NRC and the NRC telling them, we don't know anything about molten salt reactors. We would love to learn all about them and have you pay us $300 per man hour for the privilege. They said, no thanks, and did a deal in Indonesia where they're building now. And then the other one I've talked to that is taking a similar approach is Last Energy. They are more systematically shopping around to the whole world and trying to find the best venues that know that they need this power and are willing to just take no shenanigans type of approach. They have not announced anything yet, but they are optimistic about Eastern Europe. Finally, an interesting strategy would be to, rather than providing electricity at all, to use the energy to power industrial processes. Water desalination is a popular one that you'll hear about, and fuel synthesis. We can have nuclear-powered synthetic aviation fuels. The advantage of this is that you have a lot of flexibility in where to site your plant. You can put it basically anywhere, shop around for the best deal. You don't even have to worry about like what is the local electricity market or can I plug into the grid. This probably seems like a huge battle, and I think it is. You may ask whether it's even worth it. I feel that it is. Nuclear is not only an excellent opportunity for baseload power, it is also a way to power transportation, which very few other, anything that is not based on fuel. We can use it for fuel synthesis as well, and it is the energy to power space, especially if we ever get out into interstellar space. There's not enough solar out there, there's no geothermal, and there's definitely no wind. So I still see a place for nuclear in our future. Thank you, and now please welcome up Eli to talk about geothermal.
Well, thanks, Jason. I'm Eli Dourado. I'm thrilled to be here, and I think there's no better time to talk about next generation geothermal than right after Jason, because next generation geothermal is like nuclear without all of that hassle that he just talked about. I like bar charts like this that show the size of the energy reservoir. So geothermal is the big bar, and the little bar is fossil fuel. It's 4 orders of magnitude bigger energy resource than fossil fuels. It's effectively limitless. With next generation technologies, we do need some energy, some breakthroughs, some experience, but it's available anywhere in principle. It's baseload energy. It's could be cheap, and it's best of all not highly regulated. So I'm going to talk about 4 different concepts for how we could do next generation geothermal. They also essentially do the same 3 steps. They locate and access heat. They transfer that heat to a working fluid and bring it to the surface, and then they exploit the heat energy at the surface. That second step, that transferring heat to a working fluid, like that's the hard part. That's the thing that people are trying to figure out the best way to do it. So concept number one is called enhanced geothermal systems. And this is like, very similar to conventional geothermal, if you're familiar with that at all. But it starts with you drill an injection well, and you go deep until you get heat, and you inject water into that well. You drill another well, a production well, and that's the one that steam is going to come out. And then the question is like, how do you get the water from the injection well to the production well? Well, you need a porous environment down here. So if natural permeability doesn't exist, you create it through fracking. And so the water comes in, it's hot down here, it's seeping through the fractures, the high surface area, it's acquiring a lot of heat through that process, and then it comes out as steam, and you use it to power a turbine. So you engineer basically a hydrothermal resource. So the downside is with current tech, you're limited by location. It's got to be, you can go a little deeper than what's possible with conventional geothermal, but not that much deeper. And the other issue is that with the temperatures you're going to be accessing with current tech, you're limited to the energy density of subcritical steam. So the supercritical, subcritical distinction in working fluids really matters. When you get to supercritical conditions, you should be thinking like a 5 to 10x efficiency improvement. So you accumulate more energy in the fluid, and then it's also more efficient in generation. And there's a company called Fervo that is doing this approach. They just raised a B round and signed a deal with Google, so they're making progress. Second concept is called closed-loop geothermal systems. And so in this case, instead of having an injection in a production well that is connected with an open reservoir, you have a closed loop. You pump the water down in one place, flow it through pipes at depth to acquire heat, and then bring it back up in another spot. And so you're acquiring the heat in this horizontal segment at depth. The advantage of this is that you can use a fluid other than water, which can become supercritical at the temperatures that we're talking about. So you could use isobutane or CO2. Those become supercritical, so they're higher enthalpy, can transfer more heat. The downside of this approach is that you have much lower surface area of the pipes. You're limited to the surface area of the pipes. And as a consequence, the pipes at depth those horizontal segments have to be very long. And horizontal drilling is still really expensive. Nevertheless, there is a company that is trying this approach. Their name is Ever. Concept number 3 is called heat roots. And the idea here is you create a single vertical well that has a pipe in pipe. So it's going to be circulating fluid from the top all the way down to the bottom and then back up through that single shaft. But the trick here is that after you drill that vertical segment, you frack downwards. And you create a fracture network that looks like a root system. And you fill that root system from here on down with a convective and conductive fluid, and that lets you draw heat up from deeper than you were able to drill before. So at the base of the well, all that heat is concentrated and exchanged into the working fluid, and it comes back up. You can still use your supercritical fluid because the main part of the thing is a closed loop system. And a huge advantage of this is that it's very high reproducibility. All you have to do is drill deeper at any given site. You don't have to, there's not as much exploration risk. You just drill deeper until you hit the right conditions. You're able to make your well work. The downside of this is because you're limited by, you have just one vertical shaft that's at relatively low flow rate. So you're talking about maybe 10 megawatt plant. So that's kind of low power output. Maybe that doesn't matter if you can stamp out a lot of these in sort of cookie cutter fashion, just make a lot of them. And that could work. So there's a company called Sage Geosystems that raised an A round earlier this year. They're off building their first well demo that is exactly like this. The fourth concept is supercritical EGS. So that's like the first one. That's like EGS. But the difference is you use some technology breakthrough to go a lot deeper and to get access to 500 degrees C temperatures. And if you can do that, then some magic starts to happen. So this does rely on new technology. You need some new way to be able to drill more deeply to get to that really high temperature. And the solutions that people talk about are plasma drilling and millimeter wave directed energy. A huge advantage of that temperature is that you're producing steam, supercritical steam, so you can you can pipe that into existing coal turbine equipment. So you can imagine putting one of these systems at a coal plant. So your production wells are at the coal plant, and you're producing supercritical steam at the surface, and you just pipe that straight into the coal generator that is being shut down, would otherwise be shut. Like, you get the primary energy for free. This is also one that only relies on vertical drilling. It could be very high reproducibility in the sense that anywhere on Earth, you could do this if you could drill deeply enough. So it could be very cheap. There's a company at MIT that spun out of their plasma physics lab that is trying to do the millimeter wave version of this. So policy barriers, nothing like fission. It's suboptimal, but not a deal breaker. And I'll highlight two issues. So one is permitting on federal land. So if you want to drill a oil and gas well on federal land, you get approval in about 2 weeks. You don't have to go through a big environmental review process. If you want to do a geothermal well, you have to go through environmental review, and it takes about 2 years. So 2 weeks versus 2 years. Why is this? It's because the oil and gas industry lobbied for an exemption, or for a categorical exclusion to NEPA. The geothermal industry hasn't been organized enough to ask for that. Why does this matter? It's because the lowest hanging fruit for energy is all in the West, right? And that's where a lot of the federal land is. So it is very attractive as a starting point to go in those places. The subsidies for wind and solar are more generous than for geothermal. That's like another case where those lobbies have been much more effective. So I think there's really 5 buckets of technology breakthroughs that we need to make a lot of progress on this next generation geothermal. The first one is in resource characterization. So de-risking the drilling of individual wells by knowing where the heat is below the ground. So you could use big data to do this. You could use new sensors, eventually use both. Another really important one is hardening the existing drilling equipment that exists for the oil and gas industry. So these rotary drills have a lot of sensors and electronics on them. They are not optimized for the conditions that you would reach within a geothermal project. So you need to basically do some technology transfer, probably from the space industry, to harden the electronics so that they would work in geothermal conditions. Non-rotary drilling concepts like the millimeter wave, like the plasma bit, maybe also some air hammer and mud hammer stuff that would let you drill deeper and cheaper. For the 2 closed loop systems, I think specialized equipment for supercritical fluids, turbines, but also casings and coatings that would be used in the wells. And then finally, standardization of the turbines to drive down the cost of manufacturing. The number one thing we need to do to unlock progress in geothermal is get going, just work down the learning curve. We need to deploy a lot of this. Geothermal is basically a rounding error right now. Every project is bespoke, and sort of just increasing output in the industry is really important. I think that the 2 most promising concepts are the last 2 that I discussed, the heat roots and the supercritical EGS, with the difference being heat roots you can do with current tech, and the supercritical EGS you need new tech. I think it is the 5, sort of the 5 buckets of technology breakthrough that I discussed in the last slide. I think those are a good candidate for a focused research organization. I think we'll probably be hearing that a lot this weekend. And I think the goal should be at least multiple terawatts by 2040 produced by geothermal. And that is all. Questions?
Biggest bottleneck for fusion right now is cost times time of learning cycles. Imagine you could remove those constraints. What are the biggest bottlenecks?
I think it's still, you have limited personnel, like expertise, so you want to use them most effectively in things that they can work across, at maximum capacity on multiple projects at once. I think if funding were no object, that would go a long way, but yeah.
Okay, so I'll take one. Martin asks about the plants have capped profit margins incentivizing larger operations. Yeah, so I sort of touched on this very briefly or alluded to it. The utilities are regulated monopolies. It determines how they can set their prices. The prices get approved by the regulator. Essentially what it comes down to is the plant says, here is my cost, and then the regulator says, okay, I think that's a reasonable cost, so I will let you charge that cost plus a fixed profit margin. Right? So yeah, the higher your costs, the higher your profit. So in fact, the only way that nuclear gets built in the US today is in places where the local regulator says that the utility is allowed to take the costs of the nuclear construction for like a decade as it's going on, and build those into the prices that they are charging to electricity customers today, right? So if you're an electricity customer in those regions, you're getting charged like extra for 10 years for electricity that, for like capacity that they're building out. It's a really, really broken model.
For fusion especially, like there's always a debate, do you even want to patent anything? Because then you're like leaking stuff out and it's going to take like 10, 20 years before you're actually starting to deploy. So say Helion works, I think they'll have like at least a decade where the amount of specialized secret sauce that goes into their reactors, they'll have a period to really become a dominant player.
If you're doing a consumer internet company, a decade is fantastic. 6 months is enough.
Right.
But if it's a 10-year regulatory approval process or something like that, is a decade really that much?
The NRC's got to get their act together, or I think people should sell in other countries.
It's a tough question. I mean, I personally am not ready to give up on the for-profit model because I think it has so many advantages over any other model that I've encountered. But I don't have easy answers to the things you bring up.
I think that maybe like the focus research organization for geothermal, like the focus research organization that does those kind of like 5 breakthroughs, I think that should probably be nonprofit. And for deployment, you'd want for-profit, and it's mostly just paying people to do the drilling and the engineering and stuff like that. So Ryan asks, how much did typical gas fracking push us down the learning curve for these geothermal approaches? A lot. Like that's been massive. The current progress in geothermal would not be happening without the shale boom. It's just so much creativity has actually been deployed in the last 15 years in shale. That's been transformative. I think with something like the drilling equipment, right, the rotary drilling equipment, which even if you're going to use a directed energy or something, you're going to use rotary for the first bit of the vertical shaft. Like there is no market right now for a company to do the hardening that you need for that electronics. It would be very speculative for them to do that. So I think like that's a big part of it. And there's just a lot of benefits, a lot of the technologies that would benefit all different kinds of approaches. So the existing oil and gas industry, like I think that they're starting to come around to the idea of, they're going to be shut down by regulations. And this is an alternate path for basically their same skill set. A lot of it's like drilling and subsurface engineering. So it remains to be seen how far that goes, but that is where a lot of excitement is coming from.
In fission, you have some of the incumbents working against what needs to be done because they're profiting from the regulatory capture. If you relax the radiation standards, then the really profitable, cleanup projects go away. And
at the end of the day, energy is a commodity, right? And kilowatt hours are kilowatt hours. And so if you imagine a world in which you could wave a magic wand and delete all the regulatory requirements from all of these potential technologies, and you build only things that I would call it a wise, enlightened human would do, meaning you don't ignore safety, but you build to a reasonable standard of safety. And then you look at what would be the fixed and variable costs. Like, is there any good analysis out there? Do you guys have, like, what's the should cost model? Like, what is the which of these things ultimately can generate the most power for the least cost?
So fission would probably be $30 per megawatt hour or less rather than well over 100 today. It should be cheaper than coal. Geothermal in the same ballpark. Eli's got an argument for why it's cheaper in the future.
How does that compare to like solar? Like, is there a world in which nuclear beats everything else? Like, what's the best if you delete the BS?
So I think it's cheaper than solar. If you were going to power the world with it, right? Like solar can't power the world because of the intermittency. And so with solar right now, if you want to power the world, you have to build an enormous amount of batteries. And batteries are really expensive. So unless batteries get way cheaper, nuclear should be cheaper than the solar plus batteries you would need to do the same thing.
I have a funny story from fusion on this. So back when I was at ARPI, we wanted to do a decent techno-economic analysis for fusion. So we commissioned like Bechtel and some other groups to like come together and do one. First version of that, it was like $10 a watt. And we were like, guys, what the hell? But they had used like the most conservative practices from fission. And, like the buildings were like $2 a watt. And you're like, so they did a second round and they actually tried to say like, this were a new energy source. And it worked out more like $2 to $3 a watt at high capacity factor, which, then can beat solar. You got to account for like intermittency and capacity factor when you compare these sources.
So the other thing I'll add is that holes in the ground last forever. So, so you're amortizing the cost of the plant. Once you've done that after 30 years, it's like you get the primary energy for free, and you're just like replacing the equipment at the top every once in a while. So it can get very cheap if your discount rate is 0. Like if you're like a social planner, it can be pretty cheap.
Okay, from Slack, Anastasia asked, well, Eli identified some pieces of tech that would enable geothermal. Do you have a list of tech improvements that would be useful for fusion, or is it all tackled at once?
Yeah, it depends a lot on the technology. Like there's such a wide range of approaches to fusion that you have to talk about like the specific regime. I mean, there are like advancements in pulse power and more energy dense capacitors and solid state switches for the stuff I care about. High field magnets for tokamaks, like that's Commonwealth's bread and butter. Is they made a really smart way to do superconducting magnets. I think in general, like simulation tools are better now too, so that helps everyone. There's not like a single thing you could do that just makes it happen though.
Will, you mentioned that it would take about $100 million to sort of like push fusion over the line. Do you have a sense of like what the deployment curve of that money looks like? Like, is it that you start spending like $20 million, you can start spending $20 million a year, or is it like a ramp up sort of thing? Because I think that really matters to which institutional structures are best suited to tackle it.
Yeah, and again, that depends on the approach. The one that I presented was probably a couple $100 million total over 7 or so years. And that would be to build 3 to 4 specific large machines. It's a large upfront cost, like 50, 60 million bucks each. Like Zap Energy is one of the startups that it was on there. I didn't talk about it, but they are an approach that is already de-risking, and they've built a subscale thing. Now they've raised a Series B to do a break-even scale Z-pinch. But yeah, and then there's the separate question of like all of this is getting us to the point of feasibility, and then we have to. I think honestly, that's when there should be fusion startups. Is when we have a winner, and we could just make a company out of that. Like I think everyone's a little premature.
Question I continually come back to is whether there are specific applications of 5 to 10x cheaper energy which would drive the profits for one of these successes. So specifically in cryptocurrency mining, perhaps there's an opportunity to take some location which is ideal for geothermal energy, but typically with geothermal you're not next to a large energy sink, and you could create a crypto farm. If you had a large data center, if you had a desalination plant, something that would actually demand lots and lots of energy and which would take advantage of one of these applications. I guess I wonder, what do you think would be possible with 10 to 100x cheaper energy that is not being done today, that is specific enough to drive some capture of value?
I don't have a specific thought. I mean, everything uses energy. So like cheap energy would make everything cheaper. Brett Kugelmass, who's founder of Last Energy, has this argument about how like the nuclear, if it were done right, would start at like $30 a megawatt. But then if you could sort of like use the nuclear to then produce your materials cheaper, you can drive down I mean, again, a lot of that $20 to $30 a megawatt is the cost of the plant. So you could make the plant cheaper if you had cheaper materials, and you could make the materials cheaper if you had cheaper energy. And the whole thing just goes into like a virtuous cycle until, your energy is like $10 a megawatt or less.
So I think like desal is a great example. Carbon capture is a great example of something you could do. Iceland has super abundant geothermal and hydro resources, and they use it to, they're like the leading exporter per capita of aluminum. So more generally, I think like materials and stuff, like I would love to see dirt cheap like silicon carbide for aerospace, right? With a lot cheaper energy, maybe we could get that.
And I mean, there are other technologies that we'll talk about later in this conference, like nanotech, right? Which like have extremely high energy densities. If you want flying cars, that has high energy density, right? So.
Yeah, and just one more thing. Yeah, like I think, there's just a lot of processes where the system has been designed because energy is expensive, and you can relax constraints on that and make cheaper electrolyzers or cheaper desal plants. And then one funny and kind of sad good first market for nuclear power is like heating oil sands in Canada. Like to get that oil, you have to use a ton of heat. It's like stranded in the middle of nowhere. But if you had like a 100 megawatt plant that was just pumping heat underground, you could, they would like that.
Yeah, nuclear for fracking of fossil fuels is like the most ironic, application of nuclear. On that note, let's call it.